First, we need to set up the problem for overturning. If we don't consider the wall to have any lateral capacity, its own self-weight will be what resists global overturning. In reality, as lifts of slurry cure, the wall is keyed into the entire block and will gain some lateral capacity. So we can consider that those keys in the block will actually be rocks that are sitting in the wall like this and cast into the ramp fill block structure. In the large diagram below, we have the active earth pressure from the rock fill and the grout compounding on each other. We can take the same equation used for active earth pressure here, that P equals 1/2 Ka times the density times the square of the height times W, which is the width, where we'll take W, instead of taking the width of the full wall, we'll just say W equals 1 meter, because we're going to take all these values as per meter along the wall. And this time, the density and the coefficient of active earth pressure, that Ka, will actually vary. And as you remember, Ka is 1 minus sine theta over 1 plus sine theta, where theta is 30 degrees for the typical EIA soil. But however, for rock fill and grout, which both are described in a previous lecture where we got to these values, we'll take 40 degrees and 20 degrees, which leaves us the following density and Ka values I've written out over here. A quick check, however, shows that this will never work for a 3.5 meter tall wall just resisting with self-weight. That's okay. It is unlikely that 3.5 meters will be filled completely in a day. It is more likely that the ramp wall will be built in lifts in tandem with the fill, making it easier to access build the wall, as well as easier to get fill to propagate into the gets the grout mix to propagate into the rock structure. In fact, approach ramps should only be filled in 30 centimeter lifts according to the construction manual. So 30 centimeters of rock and 30 centimeters of grout slurry before moving on to the next lift. And the calculations and diagram I'll show you below will go through an example calculation for the worst case scenario, which occurs along a 30 centimeter wall, where we'll assume zero tensile capacity at the connection between the wall, the section of wall and the wall below. And we'll also distribute the load by volume. So taking the manual assumption that the fill is 85% rock and 15% grout mix, we'll extrapolate that to saying, okay, 100% of the area is the density of rock and 15% of that actually gets filled with grout. And this is applied at 1/3 of the height of the fill, which is the standard point of application for hydrostatic forces. Okay. So this diagram here shows where we're zooming into, and then we'll actually calculate the values of P rock and P grout based on that K. 1/2 Ka, the percentage that is actually filling up that area, the density with a unit conversion, the height, and the width. Once we have our P rock and P grout values, we can calculate our overturning moment at 0.00, which I have up here as the P rock plus P grout applied at that 1/3 height, and our restorative moment, which is going to be the offset of the wall, so 1/2 the 30 centimeter wall, the volume of the wall, that 1 meter tall or 3 lift tall section of wall, times its density. And ultimately, for our worst case scenario example here, we can get a factor of safety, restorative moment over overturning moment, and that's going to be 1.54. And once again, we made a lot of conservative assumptions here, so in the next section we'll move into actually looking at the capacity of the ramp wall, because it's unlikely that this will just be a one ramp wall structure teetering on top of, balancing on top of the walls below.